Hello students, welcome to the world of Intellectuals Hub. Students, today we are going to study units and measurements in physics. If you are new to the channel, please subscribe the channel for more such videos. Let's start. Measurement of any physical quantity involves comparison with a certain basic, arbitrarily chosen, internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number accompanied by a unit. Although the number of physical quantities appear to be very large, we need only a limited number of units for expressing all the physical quantities. Since they are interrelated with one another, the unit for the fundamental or base quantities are called fundamental or base unit. The unit of all other physical quantities can be expressed as combination of the base unit. Such units obtained for the derived quantities are called derived units. A complete set of these units, both the base unit and derived unit, is known as system of units. The International System of Units. In early times, scientists of different countries were using different system of units for measurements. Three such systems, the CGS system, the FPS system and the MKS system, were in use extensively till recently. The base unit for length, mass and time in these systems is as in CGS system there were centimeter, gram and second respectively. In FPS systems they were foot, pound and second respectively. In MKS systems they were meter, kilogram and second respectively. The system of unit which is at present internationally accepted for measurement is the System International Units, abbreviated as SI. The SI with standard scheme of symbols, units and abbreviations developed by the Bureau International des Sports et Measures in 1971 were recently revised by the General Conference on Weight and Measurement in November 2018. The scheme is now for international usage in scientific, technical, industrial and commercial work. Because SI units used decimal system, conversion within the system are quite simple and convenient. We shall follow the SI unit in this book. In SI, there are 7 base units as given in the table 1.1. Beside the 7 base units, there are 2 more units that are defined for plane angle as the ratio of the length of an arc, that is ds to the radius r, and the solid angle d ohm as the ratio of the intercepted area dA of the spherical surface, described about the apex O as the center to the square of its radius r as shown in the figure 1.1, A and B both respectively. The units for plane angle is radian with the symbol radian, and the unit for the solid angle is radian with the symbol SR. Both these are dimensional quantities. Note that when mole is used, the elementary entities must be specified. These entities may be atom, molecule, oil, electron, other particles are specified group of such particles. We employ units for some physical quantities that can be derived from the 7 base units. Some derived units in terms of the SI base units are given in Appendix 6.1. Since SI derived units are given special names that are shown in Appendix 6.2, and some derived SI units make use of these units with special name and the 7 base units that is given in Appendix 6.3. These are given in Appendix 6.2, 6.3 for your ready reference. Other units retained for general use are given in Table 1.2. Common SI prefix and symbols for multiples and submultiples are given in the Appendix A2. General guidelines for using symbols for physical quantities, chemical elements and nuclides are given in Appendix A7. And those for SI units and some other units are given in Appendix A8 for your guidance and ready reference. Now significant figures. As discussed above, Every measurement involves error. Thus, the result of measurement should be reported in a way that indicates the precision of measurements. Normally, the reported result of measurement is a number that includes all digits in the number that are known reliably plus the first digit that is uncertain. The reliable digit plus the first uncertain digit are known as the significant digit or significant figures. If we say the period of oscillation of a simple pendulum is 1.62 seconds, the digit 1 and 6 are reliable and certain, while the digit 2 is uncertain. Thus, a measured value has three significant figures. The length of an object reported after measurement to be 287.5 centimeter has four significant figures. The digit 287 are certain, with the digit 5 is uncertain. Clearly reporting the result of measurement that includes more digit than the significant digit is superfluous and also misleading, since it would give a wrong idea about the precision of measurement. The rule for determining the number of significant figures can be understood from the following examples. Significant figures indicate, as already mentioned, the precision of measurement, which depend on the least count of the measuring instrument. A choice of change of different unit does not change the number of significant digits or figures in the measurement. The important remark makes most of the following observation clear. First one is for example, the length 2.308 centimeter has four significant figures, but in different units the same value can be written as 0.02308 meter or 23.08 millimeter or 23080 micrometer. All these numbers have the same number of significant figures, that's digit 2308, namely 4. This shows that the location of decimal point is of no consequence in determining the number of significant figures. Here are some examples. First one is all the non-zero digits are significant. Next point is all the zeros between two non-zero digits are significant no matter where the decimal point is, if at all. If the number is less than 1, the zero on the right of the decimal place but to the left of the first non-zero digit are not significant. Similarly, another point is the terminal or trailing zero in a number without a decimal point are not significant. So for example, 123 meter is equal to 2300 centimeter is equal to 123000 micrometer has the three significant figures. The trailing zero being not significant. However, you can also see the next observation. The trailing zero, next observation is the trailing zero in a number with a decimal point are significant. The number 3.500 or 0.06900 have four significant figures each. There can be some confusion regarding the trailing zeros. Suppose a length is reported be 4.700 meter. It is evident that the zeros here are meant to convey the precision of measurements and are therefore significant. If these were not, it would be superfluous to write them explicitly. The reported measurements would have been simply the 4.7 meter. Now suppose we change units, then 4.700 meter is equal to 470.0 centimeter is equal to 4700 micrometer is equal to 0.004700 kilometer. Since the last number has trailing zeros in a number with no decimal, we would conclude erroneously from observation 1 above that the number has two significant figures while in fact it has four significant figures, and a mere change of unit cannot change the number of significant figures. Now the next point is to remove such ambiguities in determining the number of significant figures. The best way is to report every measurement in scientific notation, that is in the power of 10. In this notation, every number is expressed as a into 10 raised to power b, where a is the number between 1 to 10 and b is any positive or negative exponents of 10 to the power 10. In order to get an approximate idea of the number, we may round off the number a to 1 and to 10. Then the number can be expressed approximately as 10 raised to power b, in which the exponent b of 10 is called order of magnitude of the physical quantities. When only an estimate is required, the quantity is of the order of 10 raised to power b. For example, the diameter of the earth 1.28 into 10 raised to power 7 meter is of the order of 10 raised to power 7 meter with the order of magnitude 7. The diameter of the hydrogen atom 1.06 into 10 raised to power 10 meter minus 10 meter is of the order of 10 raised to power minus 10 meter with the order of magnitude, that is minus 10. Thus, the diameter of the earth is 17 order of magnitude larger than the hydrogen atom. It is often customary to write the decimal after the first digit. Now, the confusion mentioned in this one a above disappears. 4.700 meter is equal to 4.700 into 10 raised to power 2 centimeter, and this is equals to 4.700 into 10 raised to power 3 millimeter is equal to 4.700 into 10 raised to power minus 3 kilometer. Now, the power of 10 is irrelevant to the determination of significant figures. However, all zeros appearing in the base number in the scientific notation are significant. Each number in this case has 4 significant figures. Thus, in the scientific notation, no confusion arises about the trailing zeros in the base number a. They are always significant. The scientific notation is ideal for reporting measurements, but if this is not adopted, we use the rule adopted in the preceding example. For example, for a number greater than 1 without any decimal, the trailing zeros are not significant. For a number with a decimal, the trailing zeros are significant. Similarly, the digit 0 conventionally put on the left of the decimal for a number less than 1 is never significant. However, the zeros at the end of the such number are significant in a measurement. The multiplying or dividing factor, which is neither rounded number nor number representing measured values, are exact and have infinite number of significant digits. For example, if radius is equal to diameter by 2 or s is equal to 2 pi r, the factor 2 is an exact number and it can be written as 2.0 or 2.00 or 2.000 as required. Similarly, t is equal to t upon n, that is n is an exact number. So this is about units and measurement. I hope you like the video. Next part is in next video. Thanks for watching.